I'm Robert McMullen, and we're looking at the linear and nonlinear heat equation in case study 6 for numerical methods.
And I'm Andrew Carmedelle, and I'm doing the same thing.
There are many ways of solving PDEs using numerical methods, and the heat equation is one such PDE. There are ways such as the finite difference method, finite element analysis, Fourier analysis, and there's lots of other kind of obscure methods like decomposition and stuff like that. But for solving the heat equation, our best bet is the finite difference method, and that's because it's particularly well suited for the heat equation. We did this in problem set 3. That was just with the linear case. So we're looking at both the linear and the nonlinear case on this problem set. And just in the for background, PDEs pretty much cover all topics of engineering. You've got fluid flow, stress analysis, heat flow, all this stuff are governed by partial differential equations. And we can solve these numerically, and a lot of them we can't solve analytically. Back in problem set 5, we used Galerkin's method, which is a finite element analysis method, to do this. Now we're going back to finite difference methods, and we're going to be solving the heat equation. We're using the explicit finite difference method because it's great for simple equations because there's no integration involved and there's no matrices you have to solve, so it's very fast. It's a fairly simple algorithm, and for a pretty simple equation like the heat equation, which really has like 2 terms in it, it's very efficient, and you can get rid of the error.
Our implementation of the code was pretty much the same way that we've been doing the last previous case studies, and that on the top layer you have a lot of your housekeeping sort of code, kind of laying out the problem, saying the problem-specific numbers such as the boundary values, your boundary conditions, any other sort of things are tied specifically to the problem. From there, we call a second function which then passes the relevant information into actually doing the explicit finite difference method. In that level of code, we have basically resorting out all those values specific to the problem, and then throwing it into a loop where we would basically find the set points at a certain time and then use that time to then recalculate the next time. The way that is done is generally represented as doing a sort of T-graph. So the inner part of our code, the code specific to the explicit finite difference method, basically uses the previously calculated time step to calculate our next time, or the next heat values at the next time. A good way of representing this is by you kind of consider it as a T diagram, and that if you have a mesh size of all the nodes of the heat values that so these have like a stored heat value. To calculate the next time of the same mesh of the heat values at each node, you look at, for example, let's consider this node. You would look at the previous value at that node, along with the 2 nodes corresponding to it. This way, the iterative loop just kind of cranks out this, and so it's able to find all these values at the next mesh, and the next one, and the next one. So when you end up going to go plot it, it ends up looking, you have your boundary conditions, the initial conditions of where you kind of set it, and over time, it generally relaxes by looking at this iterative method to kind of look back and forth. Our code then takes those values, the matrix of each time step and all the heat values, to our higher level code, which then breaks it down into the relevant information for us to then plot.
Yeah.
So for the linear case, we here's an example of a nice converging plot after giving the initial conditions. You can see it's very smooth, relaxing, and the reason why it converges is because what I'm calling the convergence factor is 0.5, and that is the alpha times dt divided by dx squared. That value kind of determines whether it converges or whether it does not. So for if the convergence factor is just a little bit over 0.5, in this case 0.52, you can see it starts to converge, but it also does not fully converge, and eventually never actually reaches steady state, and instead it keeps building larger and larger until it blows up. In this plot, we consider changing the dx size, or the mesh size, for the linear case. And what this plot shows is that, which is kind of makes sense in looking back at the equation, you have the r equal to alpha dt over dx squared. That dx squared, as you make dx smaller and smaller, the convergence factor just becomes much higher, and so which can lead to instability. After running a series of these tests, you can kind of see that there's a general increasing factor, which makes sense as you start increasing the size of dx. Computational time will increase, as does the convergence factor. This red line here is the 0.5 value, which is anything below this point will converge, anything above this point will not converge. Really long. Similarly, in looking at that same idea by varying dt, or it's basically your step size, it's a very standard progression of, as your computational time increases, so too or your convergence factor decreases, because it is becoming much more accurate for a given mesh size and alpha value.
To go from the linear case of the heat equation to the nonlinear, basically the only thing that's changing here is this is the linear case, this is the nonlinear, is our coefficient for the second derivative. And the way that we're going to deal with that, since this is an iterative method, we know phi of the last step. So we can just use the previous phi to recalculate this value. And then we put that in. So we don't actually have to do any sort of root finding or any additional computation to find this. Since we're going through iterations, we just use the previous one. And that keeps it simple and fast. These are results for the nonlinear case. This is one of our first tries. These are just some values we made up for the dt and for the for our mesh. And you can see it gets a little bit worried. It's a little bit unstable there, but then it evens out and we end up with a good result. We can pretty easily fix this by making our dt just a little bit smaller. We can increase the stability and we'll see a much better result. It's going to run a little bit longer too. And so we can see it's cooling off right there. And that's the nonlinear equation. To look at the characteristics of the nonlinear equation, we made a little script that runs through a bunch of different meshes for the X mesh of points, and it's going from 11 to 19. So these all start out at our initial condition, but basically this gives us more resolution the more number of points we have. And so the way we calculate the error here is we evaluated the function for a set amount of time, and then at the end of this time we took the equation, which was a heat versus x plot, and we integrated it to get the area under it. And then we compared this to the same thing for a different number of mesh points. So the reason we took the integral was because they each had different number of points, and they're very difficult to compare that way. Taking the integral, you get the area. The area should be the same if they have the same exact answer. So this is really showing the relative error because it's between two answers with a different mesh. And so we can see as the number of mesh points we have goes up, the error goes down. This is a log scale on the left, so it's decreasing quite rapidly with the number of mesh points. And so you can see that increasing the number of mesh points really is a very effective way of getting your error down. However, if you increase it too high, you will hit a unstable function, and then you can't go any higher without changing your dt. Yeah.
So what we've determined by going through this case study is that the explicit finite difference method really works well if you're very smart in choosing your step size of your time step, your dt, and the number of nodes in your mesh, or your dx value. And that if you want to become very, very accurate, there is a very strong increase in the computational time as you increase your dt, but that also greatly increases your convergence factor, and just the overall error is decreased as you increase your dt. Similarly, as you increase dx, you can have a much less error in your code, but if you make it too small of a value, it will no longer converge and it will just not work and not run. So that's kind of but overall it's a good method. It converges, finds a pretty good solution, and the underlying theory behind it is very simple and very easy to implement.
I'm Robert McMullen, and this is Andrew Carmedelle, and this was case study 6 for numerical methods.
Thanks for watching.